Good morning, Year 11. This is your C2 Pep Talk. Could you kindly have a look at the formulae in the front here? Have a look at some of the things you may need to utilize during the exam. You'll be given a periodic table at the back of the form. Don't forget to look at it and use it for some of the questions you'll be seeing. I'll show you boxes, specifically this box here, with respect to formulae that are going to be useful for the C2 exam throughout the next few PowerPoint slides. So let's move on. So we'll begin with the collision theory. You should know that when particles collide, they must have a minimum amount of energy. That's the activation energy required for a reaction to occur, and they must be facing the correct orientation, facing the right way. Now, when particles collide, if they react, reaction occurs. If they don't, they'll bounce away from each other. So activation energy, minimum amount of energy required, and the correct orientation. What factors affect the rate of a chemical reaction? You've got temperature, because particles will simply move faster with more energy, and therefore they're going to collide more frequently, and therefore there are going to be more successful collisions. Concentration also increases the rate of reaction, because the more particles you have in a given area or a given volume of a solution, the more the collisions will occur, therefore more successful collisions. Pressure increases the number of collisions in a particular area, a particular volume, and as a result more particles in a given area reacting, increased rate of reaction. Surface area exposes more particles so they can collide more, again more collisions, more reactions. Now what does a catalyst do? It simply lowers the activation energy, that's the minimum energy required for a reaction to occur. So here we're seeing a graph of the experiment shown at the top. Magnesium ribbon, a metal in an acid, dilute hydrochloric acid, conical flask, the gas of hydrogen that's produced is being collected in a syringe, and the results are shown in this table here. So you can collect the volume of a product, for instance a gas, and that will tell you over time whether you're collecting lots of gas or a little bit of gas, whether the reaction is going fast or slow. You could plot a graph, here the volume of hydrogen being collected with time, the gradient of the graph, change in y by change in x, the slope tells you the rate of reaction, and as you see it starts to slow down here, less gradient, and then it plateaus, becomes flat, illustrating the reaction has stopped. The reason probably is because one of the reactants has been used up. And here's another example here of a mixture where a reaction's occurring. There's an X drawn underneath the beaker. As the reaction occurs, the mixture becomes more cloudy, and you're timing to see how long it takes for that X to disappear. The quicker it disappears, the quicker the reaction must be going. You could, for instance, have a thermometer, change the temperature of the reaction and see how quickly the X disappears, i.e. how quickly the reaction occurs. So when you're looking at the rate of reaction, what you're looking to see is the amount of reactant that's being used up divided by the time it took to use it up, or of course the amount of product being formed and how long it took for that product to be made. Remember, on a graph, the slope of the graph, change in y by change in x, tells you the reaction is occurring. You've got a reaction that's at its fastest when it's first started because there's loads of particles reacting. It slows down as you start to use up the reactant and eventually stops when one of the reactants has been used up. So we must also remember pure substances are ones that have a single type of substance in it, whether it's an element or a compound. A pure substance has a very specific melting point and a boiling point. Now what you could do is, if an impurity exists in a sample, it would lower the melting point. This experiment, distillation, very important. You've got a mixture here, you've got a salt dissolved in water. To separate it, you heat the liquid, it evaporates, goes into a condenser, water's going in and then out to cool the pipe. It doesn't actually touch what's inside, and the water vapor, the gas, condenses and falls separately as pure water. Chromatography, very important. You've got a chromatography paper put into a beaker with a pencil line drawn and a sample. The sample is then allowed with a solution. As the solution rises, the solvent rises, it will take the sample with it, i.e. the different parts of the sample. Now what could happen is you might have a substance that's made of just one, so there's one dot shown. The RF value is the distance moved by the component that's found in your sample, i.e. the thing that you can see moving in the chromatography paper, divided by the distance moved by the solvent front. You could be shown an example like this, where you've got a pure drug, that's shown here, only one type of substance present. You could have 3 different samples, and as you can see, A does not contain the pure drug, B has the pure drug but something else in it as well, C only has the pure drug. You must be able to interpret chromatography, and when you're interpreting it, keep in mind the paper is what's called a stationary phase. It's the bit that's not moving. The water or the solvent is the mobile phase. Smaller substances and those that associate more with the mobile phase, they bind more to the solvent as it's moving, will end up moving further up. If something is a larger compound and it doesn't dissolve very well in the solvent, it wouldn't move as high up. Key thing, RF value, look at how you calculate it, and don't forget how you interpret chromatography. Next on the agenda we have the tests for the different gases. Carbon dioxide, you bubble it through lime water, it becomes cloudy. Lime water, remember, is colourless. Adding carbon dioxide gas to it makes it cloudy. That's the positive of the test. Chlorine, as a gas, will bleach damp blue litmus paper. So your blue litmus paper will become red and then white, i.e. it's lost its colour, if chlorine gas is present. Test for hydrogen gas. You have something that contains hydrogen gas. You place a lit splint, so that's one with the flame still on it, into the neck of the test tube, and a squeaky pop sound is heard. Of course, for water you can simply put it on cobalt chloride paper and it will go from blue to pink. Oxygen. If you were to have oxygen gas in a test tube, you would get a glowing splint. That's one that you lit, you blew it out so it's still a little hot, put it at the end of the test tube, and it should relight, indicating that oxygen is present. So the test for carbon dioxide, chlorine gas, hydrogen, water of course, and oxygen gas as well. You can't forget about other gases. You should know that chlorine gas is a pale green gas, bromine is a brown, reddy gas when it's warmed, and iodine very quickly goes from solid to a purple gas. The flame tests for triple, lithium is a crimson, sodium is a yellow, potassium is lilac, calcium gives you an orange red, and copper gives you green. Don't forget these colours. Flame test can occur where you add heat from a Bunsen burner on the blue hot flame. The electrons get excited, and when they fall back down to their ground state, their original state, they release the energy as a particular wavelength of light, which is why you see the different colours for the different elements. Their electrons jumped to different levels and therefore gave out a very particular colour inside the blue flame when the metal was passed over it. You can get a piece of wire, a nichrome wire, a loop, with a solution that contains these metals, place it through a blue flame and look to see what colour the flame is. Those that are doing combined, keep an eye on the gases, the test for the gases and water, and of course those doing triple, keep an eye also on the flame test. Flame emission spectroscopy I'm showing you here. Every element, these metals shown here, will give a very specific emission, release of energy in particular wavelengths of light, and you can match an unknown element to the different patterns shown in a standard table. So here for instance the top one matches strontium, so your unknown sample happens to be strontium. We should never enter a C2 exam without being comfortable with the basics of a greener world around us. So the sun sends in its energy through solar radiation, the light comes in, it's absorbed and then re-released, or you could say re-radiated as infrared. That infrared moves up and then is absorbed by the greenhouse gases. So by adding more carbon dioxide to the atmosphere, such as burning fossil fuels, more factories, deforestation, which should have removed some of that CO2, agriculture, decomposition of rubbish, etc., loads of ways that we're contributing more CO2 into the atmosphere. This is going to lead to the polar ice caps melting. That can lead to flooding, drought, extreme weather changes. That would affect agriculture, the amount of land we have to live on. also affects the migration of insects, so diseases move around the planet, and of course food chains of different animals and plants are then upset as well. The carbon footprint reflects the amount of carbon dioxide and other greenhouse gases that are being emitted over the full life cycle of a product. We can reduce our emissions, as shown here in this list, by car sharing, educating people, less waste and therefore less energy, making our homes and our industries more efficient, recycle substances, use more renewable energy, etc. So your green chemistry is very important for your C2 exam. This brings us neatly towards our last slides. We're looking very quickly here at the atmosphere of the Earth. It starts off with lots of CO2 in the atmosphere. Volcanic activity contributes ammonia and methane and of course some water vapor. Soon as the Earth's temperature starts to cool, the water vapor becomes liquid water, the oceans. CO2 dissolves into those oceans and creates rocks and sediment, and that also creates more CO2 trapping into the rocks. With time, as the oceans develop and the CO2 is trapped, life begins to evolve. There's no oxygen in the atmosphere, so there's a lot of anaerobic respiration going on. But as life starts to evolve, photosynthesis starts to occur. That also removes CO2 and contributes oxygen to the atmosphere. Some of that CO2 was dissolved in the water, now is being used by photosynthesis, and of course was trapped into rocks. Some of the life that trapped the CO2 is also going to have died and either decomposed or got trapped under rocks and formed oil over millions of years. With time, the amount of oxygen increased, the amount of nitrogen increased, and the CO2 levels fell. So the Earth's atmosphere has evolved, and there's evidence that supports it. When you hear of a theory, you have to know, is there evidence to support it? And if the theory's changed, it's probably because the evidence has changed. Now, hydrocarbons, a quick mention for those. Crude oil contains a variety of hydrocarbons. You put them into a fractional distillation column. Bigger hydrocarbons stay nearer the bottom because they have a larger boiling point due to their higher intermolecular forces between the molecules. Smaller hydrocarbons rise to upper levels where it's cooler. They condense at different levels. By having a separation of hydrocarbons, you can use them for different things. So the boiling points and the viscosity, so how easily it flows, increases down the groups. Here, down the fractional distillation column, larger groups of hydrocarbons, a bigger boiling point, more viscosity. And of course, likewise, the smaller ones nearer the top, they will condense separately and they will have a lower boiling point, weaker intermolecular forces, and less viscosity. Equilibrium is our final mention before I release you for your exam. Equilibrium is when a reversible reaction occurs in a closed system. The rate of forward and the reverse reaction are equal, so the concentrations appear to be stable, but you do have reactions forward and reverse going on at the same time. If you were to increase the temperature, the reaction wants to go in the endothermic direction. If you lower the temperature, the reaction will shift or move in the exothermic direction. If you increase the pressure, the reaction shifts to the side with less gaseous molecules. If you lower the pressure, the reaction moves to the side with more gaseous molecules. So take a moment to think about this box, think about the atmosphere and how it's evolved, and don't forget hydrocarbons in fractional distillation, why they're separated based on intermolecular forces. And that brings us to our final slide here, a recap of those formulae that are shown here. Equilibrium I've left for you on the page for you to think about as a last piece of advice. Remember, 1 minute per mark. Use your time wisely. You're not here to invent the science. You are here to simply use the science you've been taught that's already established. Think about the application, think about answering every question, look at the marks, tick one box if it says so. Examiner gives you plenty of information that will help you answer all the questions. Good luck. Remember to wait until you are dismissed class by class. Thank you very much for your time.